Okay, and once you define the trig functions, the next question immediately becomes, how do you evaluate them at given angles, right? At least theoretically, it's a lot easier to just say the definition of the trig functions sine, cos, and tan, right? You can write them down in terms of the coordinates of the terminal point, but that assumes that you have access to the coordinates of the terminal point, and that they might actually be difficult to find in general. For an arbitrary value of theta, it might be difficult to get the coordinates of that terminal point. So that's what we're going to talk about now on this page, is a few techniques for doing that. So to start with, it helps to be able to evaluate sine, cos, and tan at these fundamental angles. So you got 0, pi over 6, pi over 4, pi over 3, and pi over 2. And again, those are called fundamental angles, or at least I call them that. So I'll refer to them as the fundamental angles in this course. So in order to do that, in order to evaluate sine, cos, and tan at these angles, here's a trick. Now, there's several methods to do this. This is the one I prefer, and I think it's very easy to communicate, and I think it's very easy to use, and it's very easy to remember. So that's what I like about this method. This is an alternative to the special triangles. A lot of people like the special triangles. If those work for you, fantastic, keep using those. But here's another tool that you can put in your tool belt as well, just giving you another option. So the way you would set up this table, which is what I call this the table method, because it follows a table, is you set it up the following way. You're going to make 4 columns, one for theta, one for sine of theta, one for cos of theta, and one for tan of theta. Okay, so we're going to make a table here. And the first column, underneath theta, you're going to include all the fundamental angles in this list. So from the smallest to largest, you've got 0, pi over 6, pi over 4, pi over 3, and pi over 2. Okay, so now what we'll do is we'll fill in the sine column. And it's a really neat pattern that this follows. I'm just going to add a couple more lines here to keep the table looking like a table. But okay, let's figure out the value of sine of 0, right? The value I put here is really going to be sine of theta when theta is equal to 0. And then the value that I put here will be sine of theta when theta is equal to pi over 6, and so on. Okay, so the way we fill in these values is start by writing the numbers 0, 1, 2, 3, and 4. Then what you're going to do is take the square root of each one. So I'm going to take the square root of 0, take the square root of 1, square root of 2, square root of 3, and the square root of 4. Then I divide each of those values by 2. See the pattern? It's really easy to remember this pattern for that reason. Just go 0, 1, 2, 3, 4, square root each one, and then divide each one by 2. And then now, once you get to that point, now just pick off the ones that can be simplified a bit, right? Because the square root is 0 over 2. Nobody would write a number like this, right? It's 0. Square root of 0 is just 0. Then you divide by 2, it's still going to be 0. So let's just simplify this to being 0. The square root of 1 over 2, well, square root of 1 is just 1, so that's going to be 1 over 2, or in other words, a half. So it's a half is the actual value that you want. Root 2 over 2 and root 3 over 2, there's not much you can do with those. You can play with the form a bit, but there's no advantage to doing that, so there's no point in changing them at all. Just leave them in the way they are. This is as good as it gets for those values. Sine of pi over 4 is root 2 over 2, and sine of pi over 3 is root 3 over 2. But root 4 over 2, you can simplify that a bit because the square root of 4 is just 2. So you have 2 over 2, which is 1. Okay, so that's the brunt of the work is already done, because now we've got the sine column filled in. We can just fill in the cosine column by just writing the exact same values in reverse. So start with the largest and put it at the top. Then we'll put root 3 over 2. Then we'll put root 2 over 2. And then we'll put 1/2. And then we'll put 0. So it's the exact same values, but in reverse. And then to fill in the tan column, well, remember, tan of theta is sine theta divided by cos theta. So you can just go 0 divided by 1 is 0. 1/2 divided by root 3 over 2. Do the fraction division carefully, but you're going to end up getting 1 over root 3. Tan of pi over 4, you're going to have root 2 over 2 divided by root 2 over 2. Anything divided by itself is 1, right? So you don't even have to do the calculations. Tan of pi over 3, you've got root 3 over 2 divided by 1/2. That's going to be root 3. And then finally, tan of pi over 2, that's going to be 1 divided by 0. Well, you can't divide by 0, right? That's not defined. And in fact, pi over 2 is one of the places where tan has a vertical asymptote. And once we get down to the graphs, I'll remind you of that fact, but that's no surprise that the tan of pi over 2 is undefined. Okay, some additional notes that I'll make about these functions. First one is that sine and cosine are both what is called 2 pi periodic. So sine and cos are 2 pi periodic. Okay, so what does that mean exactly? It means they repeat every 2 pi. So in other words, sine of x plus 2 pi is equal to sine of x for every real number x. Okay, that's what that means. Or that's how to finish this. So it's not just for one number x. This is true no matter what value of x you take in the real number system. So I'm actually going to introduce an abbreviation here. A lot of times I'd write for every x in the reals, but here I'm going to just use the for all symbol. So this is for all x in the reals, or for every, or for all. So let me just put a note up here. It's like an upside down capital A. This just means for all or for every. Same thing, right? That's what that means. For all or for every. Just a nice little abbreviation you can use to make mathematical statements shorter, but yet still keep them precise, because we like to do that. Okay, so that's what that means. But you could say the same thing about cosine. So let's just practice writing this down. So for cosine, you'd have cosine of x plus 2 pi is equal to cosine of x, and that's also true for all x in the reals, for all real numbers x. And then the other note I'm going to make is about the tan function. And you might guess that tan is 2 pi periodic as well. And in some sense it is. It does repeat every 2 pi, but you can actually even say more. You can say that tan is pi periodic. It actually repeats more often than sine and cos. In fact, it repeats twice as often. So tan is pi periodic. So again, I'll underline that because that's an important term. And what that means is that tan of x plus pi is equal to tan of x. And that's again also true for all x in the reals. I guess I'll put periods on those sentences as well. Okay, so that's the periodicity of sine, cos, and tan. So we know what sine, cos, and tan are at the fundamental angles, but you actually have more than that because of the fact that sine and cos and tan are periodic functions. Okay, so now let's talk about the graphs. So let's do the graphs of y equals sine of x, y equals cosine of x, and we'll do the graph for y equals tan of x. Okay, so I've got graphs already here. We can just fill them in. So this is what the graph of sine looks like. It starts at the origin and it goes up to actually +1 and -1. That's the maximum value for sine is 1 and the minimum value is -1. And it's going to go up and down and up like that. That's called a sine wave. And it hits its peak at pi over 2. It hits the x-axis right here at pi. I won't label that just because I don't want it to get in the way of the graph. And then here it hits its bottom peak at 3 pi over 2, which I'm going to write above the x-axis. Okay, and then here, right at 2 pi, is when it comes back to 0, and then it just starts to repeat. So this is the fundamental sine wave, and if you go beyond 0 to the left or beyond 2 pi to the right, it just repeats the exact same pattern. So I'll just emphasize that in green. I'll just draw the repetitive part in green. But as long as you understand the fundamental behavior of sine between 0 and 2 pi, just know that it repeats beyond that, and you have everything else you need. And then for cosine, well, it also has a peak of 1 and a minimum peak or valley at -1 along the y-axis. But it doesn't start at the origin. It's basically the same thing as the sine wave, just shifted, everything's shifted over to the left by pi over 2. So it hits its peak right on the y-axis, and then it goes down and hits the x-axis right at pi over 2. And then at pi, that's where cosine hits -1, and then it comes back up, hits the x-axis right at 3 pi over 2, and then comes back up and hits its peak again at 2 pi. Okay, so that's the fundamental wave for cosine, and then again it repeats the same pattern on either end. Okay, so that's what the cosine function looks like. Tan is a little bit more exciting because you've got a couple of vertical asymptotes. You've got at least 2 that will draw, but there's actually infinitely many vertical asymptotes. One of them is actually at the x value pi over 2, right? Because tan is undefined at pi over 2. So you've got a vertical asymptote here. You've actually got another vertical asymptote at negative pi over 2 because tan is pi periodic, right? So we've actually got a vertical asymptote here, and then at negative pi over 2 we've also got a vertical asymptote. Tan goes through the origin. It explodes upward like that. It gets very, very large as x gets close to pi over 2 from this direction. The function just keeps on growing. And then as x gets close to negative pi over 2, the function just explodes in the downward direction. And again, beyond that, it just repeats. So over here, you have another piece of the next segment. And then on this end, you've got another piece down here. Okay, but it just repeats that. This is the fundamental wave. So just take a copy of this, and you put another copy here, another copy here, and so on. It just goes on forever in both directions. Okay, so those are the graphs of sine, cos, and tan. I won't do the graphs of the reciprocal trig functions, but you can draw those graphs with certain techniques as well, but I won't get into that in this section. This is just a very rough review. Okay, so let's do a couple of examples where we evaluate trig functions at certain angles. So for part A, we don't have to do much work. So I'm just going to sneak it in up here because we need most of this room we'll need for part B. So for part A, we have sine of pi over 3. Okay, well, pi over 3 happens to be one of the fundamental angles, right? It's in the table, sine of pi over 3, or pi over 3 is in the table. So sine of pi over 3 is just root 3 over 2. It's that easy. So if the angle that you're dealing with, or that you're given, is one of the fundamental angles, then you can just get your answer right from the table. So we can just say sine of pi over 3 is equal to root 3 over 2. And you're done. There's not much more to it. Okay, but for the second one, cosine of 11 pi over 4, that's going to be the majority of our work here. That's going to take a little bit more. So the first thing you want to do is try to reduce this somehow. And here's what I mean. Make the observation that 11 pi over 4, let me rewrite that a little differently. Let me write that as 8 pi plus 3 pi all over 4. Right, I can certainly do that. 11 pi is equal to 8 pi plus 3 pi. But I can also now split this up and make it 8 pi over 4 plus 3 pi over 4. Okay, and why did I do that? Why did I break the 11 into 8 plus 3? Because 8 is a multiple of 4, so this actually reduces really nicely, and I get 2 pi plus 3 pi over 4. And if you think about it, let me draw a sketch of the unit circle down here. Because remember, in order to evaluate trig functions at angles, we need to be able to find the coordinates of the terminal points. That's really what this comes down to. So if you want to find cosine of 11 pi over 4, you would need the x-coordinate of its terminal point. So what is the terminal point of 11 pi over 4? Well, it's a little bit harder to identify than if you look over here, right? 2 pi, remember 2 pi is the circumference of the circle. So 2 pi means go once around the circle, and then 3 pi over 4 means go 3/4 of a pi again, and then you're done. Remember, pi is halfway around the circle, because if 2 pi is all the way around the circle, then pi must be halfway around the circle. So 3/4 of a pi is actually 3/4 of halfway around the circle. So this is actually the terminal point for this angle. Okay, so let me draw that. Here's what we have. Draw the ray going out. And let me just really emphasize that as far as the terminal point is concerned, this 2 pi is irrelevant, right? What difference does it make? If I just go, I'm starting here anyway, right? You always start here. If I go 3/4 of a pi, I'll end up here. If I go 2 pi plus 3/4 of a pi, I'll still end up here. I'll cross this, I'll traverse the circle one extra time before getting there. But that doesn't change the fact that this is the terminal point. Okay? So here's your strategy. We might as well just work with theta equals 3 pi over 4 because of the fact that that 2 pi is irrelevant. Okay, so our next step, and let me actually just shade that in here to make it clear what I'm talking about. That's our theta, and I'm just, to make it really clear, I'm talking about this entire angle here. That is your theta. But that's still definitely not going to be in our table because it's more than 90 degrees, or in radians it's more than pi over 2. But the largest value in our table is pi over 2. So we're still not going to be able to get the answer from the table here, but we're going to look for something called the reference angle. So the reference angle, which you don't have to write this if you don't want to, but I like to, just for the moment, to avoid any confusion, I'm going to denote it with theta and put a hat over top. And the reference angle is this thing down here. It's the other part of the pi, right? This is your reference angle. So that's, well, if halfway around the circle is pi, and this was 3/4 of a pi, this must be 1/4 of a pi. So we can say that theta hat is equal to pi over 4. This is the reference angle. Okay, and formally what the reference angle is it's the distance from the terminal point to the x-axis along the unit circle, but in the shortest way possible, right? So I wouldn't measure the reference angle as this distance, I'd measure the reference angle as this distance. So it's the distance from the terminal point to the x-axis along the unit circle, which is equivalent to just whatever this angle is, which is pi over 4. Okay, so now here's what you know. Here's what you can say. We're almost done. We can say cosine of 11 pi over 4. Well, that's equal to cos of 3 pi over 4, right? Because this 2 pi was irrelevant. But now here's what you'd know. Because theta hat equals pi over 4 is the reference angle of 3 pi over 4, we know that this is either equal to plus or minus the cosine of pi over 4. So the cosine of any angle and the cosine of its reference angle can differ only by sign. That's the important logic that we're using here. So that's why I get to put a plus or minus here. That's the important feature of reference angles. And cos of pi over 4, the reference angle, pi over 4, is actually one of the fundamental angles. So we can determine what cos of pi over 4 is by looking at the table. It's root 2 over 2. Okay, so this is going to be plus or minus root 2 over 2. All that's left is to determine which one it is. So our answer, we're not done here. We still don't know the answer. It's either plus root 2 over 2, like the positive number, or it's negative root 2 over 2. But it's still up to us to figure out which one. And here's how you can do it. There's something else I want to add to this picture down here. Remember, where is the previous page? Oh, well, anyways, remember that sine, cos, and tan were defined in terms of the coordinates of a terminal point. So in this quadrant, any terminal point that ends up in this quadrant, both its x and y coordinates are going to be positive. So sine, cos, and tan are all going to be positive. But if I move now over into the second quadrant, well, now the y coordinates are all positive here. But the x coordinates are negative because we're to the left of the y-axis. These are all negative x values. But the y coordinates of every point in this segment of the unit circle are all positive. So sine is positive, but cosine is negative, which also means that tan is negative. So the only function out of the 3 fundamental trig functions, sine, cos, and tan, that's positive in this quadrant is sine. But down here, both the x and the y coordinates of all these terminal points are negative. So that means sine and cos are both negative, but if tan is their ratio, then tan is going to be positive. So that's how you know that tan is the only positive function down here. And lastly over here, the x coordinates are all positive here, but the y coordinates are negative since the points are below the x-axis. So that means sine is negative, but cos is positive. And again, since tan is the ratio, that would make tan the ratio of a negative divided by a positive, which would be a negative. So the only function that's positive here is cosine. And you don't have to go through that every time. There's a nice little memory trick. You can, if you start in the first quadrant and go counterclockwise, you can remember all soup turns cold. And I think there are other acronyms you can use too if you like them better. Or some people like to start down here, go counterclockwise, and read this as the word cast. Some people call this the cast method. But however you want to remember it is completely fine with me. Just make sure that you can remember it somehow, or just reinvent it by considering the sign of each of the coordinates and thinking about what sine, cos, and tan really mean. But really, we're done here now, right? Because we know our terminal point is in this quadrant, and if sine is the only function that's positive in this quadrant, that means cosine must be negative. So since cosine is the function we're dealing with, that is how we finish it. So we can say, therefore, cos of 11 pi over 4 is equal to negative root 2 over 2. So that is actually what's going on there. There's an awful lot of work and thinking that goes into this, and you aren't necessarily going to write all this down every time you evaluate a trig function. But if I were going to explain to someone how to evaluate trig functions at points, this is what I would tell them. But a lot of times after you do it enough, this whole process gets internalized, and you can do it in a few lines. So don't be intimidated if you're comfortable doing this and you don't show all these steps. That's fine with me. But if you forget how to do it, if you forget how to evaluate things like this, this is the line of reasoning that you would use.